we're moving on to the next body system, or systems, excuse me. Some books consider the muscular system and the skeletal system to be separate. A lot of them combine them into the skeletomuscular system, since the muscles have to anchor on the bones, and the skeleton isn't much use without the muscles pulling it around. So we're going to cover them as a combined unit, but we're going to kind of cover them separately anyway. So, muscles, we've talked about this before when we talked about tissues, are very long cells. Your cells run from kind of the end. There's connective tissue wrapped around the fibers and around the muscle itself. And as you get to the end, there's a lot less muscle and a lot more connective tissue until there is only connective tissue. These are tendons. There it is. Muscle itself does not attach to bone particularly well. You need connective tissue to attach it to the bone. And that's what the connective tissue does. There are contact points, what they call origins and insertions, but basically a point where the muscle is anchored and a point where the muscle is pulling on something and making it move. Is it for your biceps, it's pulling your lower arm up. For your triceps on this side, it's going around the corner and pulling on your elbow and moving. And that's the way muscles work, right? They always pull, they don't push. And once you've contracted one, in order to use it again, you have to stretch it back out, which means you got another muscle pulling it to stretch it. So you get a lot of opposition in muscles. Okay, let me do this. I'm getting cheap. I'm using as little of this as I can get away with. Now, when muscles move things, they can be contributing to the movement in different ways. When I bend my arm, the prime mover, the muscle that is most making that happen, is here. It's your bicep. But when I pull my arm, there's a muscle here that's really, its prime mover job is to rotate your lower arm, but it also stabilizes your arm when you bend it. So it's helping. That's what a synergist is. A synergist is a muscle that is not doing the bulk of the work, but it's helping the work happen. And a lot of our muscle movements involve more than one muscle making the movement happen. It involves, a major muscle, a prime mover, and some helper muscles who are prime movers usually for other more subtle actions. Obviously, you can damage your muscles. You can pull them, which is partly a connective tissue issue. You can strain them, which is a little bit worse. You can tear them, which is definitely a muscle issue. And all of these have different levels of recovery and different levels of effects on your ability to use that muscle. And if you've torn the muscle, you gotta not use it for a while. If you've strained the muscle, a lot of times you need to back off using it. If you've pulled the muscle, now strain you can use as long as you don't push it. Pulls are a little bit worse. Sorry, I'm looking at the screen backwards, it's confusing me. Sometimes your muscles tighten up for no apparent reason. Now, there are conditions that cause this, changes in like potassium levels and magnesium levels and other kinds of things. But to a large extent, no one is entirely sure what causes major muscle cramps. Abdominal cramps are different, right? Those are, you're pushing stuff through your digestive system quickly as an attempt to move something bad out. But surface skeletal muscle cramps, yeah, if you use the muscle too quickly or you use it under bad temperature conditions sometimes, but sometimes you just get cramps, and some people are prone to cramps, like when you're sleeping. You know, your foot tightens up, your leg cramps. And there are an infinite number of fixes for that. If you tell people you know that you're having, you gotten foot cramps in the middle of the night, or you're having this cramp, or you're having that cramp, is that you will get a whole array of different, oh, you gotta do this, you gotta do that. A cramp is a spasm. It's a tensing of the muscle. And I mean, one thing that does work is massaging the muscle, is basically physically trying to stretch the muscle back out by, rubbing it to try to stretch it back out. But most people are trying to tell you something that's like, this will prevent it. Drink more water. Make sure you got more potassium in your diet. Breathe into a paper bag. I used to fence with somebody who was told that it had to do with, he needed more carbon dioxide in his blood. May have been carbon monoxide. It didn't make any sense, so I don't know which one it was. And he would breathe into a little paper bag in order to keep himself from cramping up when he was fencing. Since it is somewhat associated with relaxation, it's quite possible that a lot of these fixes are placebo effects that are actual effects, because placebo effects are mental, relaxation is mental, and that also tends, I think, to be why a lot of these fixes work for a while, where you kind of expect it to work. It kind of keeps the muscles a little bit more relaxed, even when you're sleeping. And then, eventually you start to get an occasional cramp, and you go, it's still mostly working. And you don't realize they're at the same rate that they were before. It's just, or sometimes they come back and you go, I gotta change to something else. But all of these fixes that people give you don't tend to stand up to testing. When you go, well, does this really work and does that really work? It's hard to tell. One thing your muscles do that's kind of weird is they can build up an oxygen debt. When we break down glucose in our cells and use it to move the energy into ATP, there's actually two stages to it, and only the last stage uses oxygen. The first stage is anaerobic, doesn't use oxygen. It's like our distant ancestral approach to getting energy. And it doesn't do a great job of it, but it gets some energy by basically breaking the glucose molecule in half. And then the oxygen part breaks all the carbons apart from that and gets way more energy. However, if you need your muscles and you're breathing and your heart's beating, but you're not quite getting enough oxygen to your muscles to keep them running the way you need them to run, they will go into oxygen debt. They are the only normal cells in your body that will do this. You cut the oxygen off to your brain cells, they're in trouble. You cut your oxygen off to almost any other cells, but muscle cells will go into oxygen debt. They will do the first part of respiration. They will build up lactic acid as kind of a product that's eventually going to get fed into the oxygen using part, and that's why you're building up an oxygen debt. So you're walking in the woods and you look up the trail a little bit and you see a grizzly bear, and you're thinking, ooh, a grizzly bear. And let's be honest, you're thinking, I gotta get my phone out. Then the grizzly bear takes a look at you and you realize from the look on his face, he's going, oh, lunch. And it's time to take off. get back to the car, or get up a tree that a grizzly bear can't climb, or get the hell out of Dodge somehow. And you're running and running and running, and your muscles are working and working and working, and your heart's pumping, and you're breathing really hard, but you start to overuse your muscles. The oxygen supply just can't keep up. That's oxygen debt. And so you get into the car, or you get into the cabin, or you get up the right tree where the grizzly bears, can't quite get to you. What do? You sit there. You've got to pay off the oxygen debt. You've got to take that lactic acid, fiddle with it a little bit, put it into the aerobic part of your respiration, break it all the way down to carbon dioxide, because you don't want it building up. Because lactic acid is not horrendously poisonous, but it isn't a great thing to have hanging around your cells. I've said it's the only normal cells that do this. There are other cells that can do this, can activate this ability. When a tumor starts to grow, a localized tumor, when it gets big, as it gets bigger, the cells in the middle are a long way from the blood vessels going around the outside of the tumor. So the oxygen supply to the inside of the tumor goes down quite a bit. Nutrients too, but that's not a big deal. Now tumors, remember I've said this when I talked about cancer, is because they're genetically weird, is that they are activating and deactivating genes kind of randomly. It's a mutational effect. And a successful tumor, which means it continues to live, will activate one of two systems, or maybe both systems. One system is a system that activates when you're a growing embryo and child, and you're making new tissue, and you need blood vessels to get into the new tissue. And so chemicals are released to say to new blood vessels, come here, give us some capillaries. We're building new tissue here. We need it fed with blood. Some tumors will activate that, and blood vessels will actually invade the tumors to feed them. There's actually chemotherapy drugs that counteract that chemical. It's a good thing because, if you're a full adult, you're not making that stuff. You're not making new tissue. You don't need to have that chemical activated. So turning it off is not really a bad thing, side effect wise. But some of the cells sometimes turn on the oxygen debt system. So they can continue to survive on very low levels of oxygen. They do build up lactic acid, and lactic acid gets carried off in your plasma. It kind of comes out of the tumor eventually. But you don't want that. You don't want your tumor to have a success, but it is one of the potential issues. Oh, wow. Sorry. Flashbacks to teaching anatomy and physiology. A lot of bones. Now, your skeletal system doesn't include your cardiac muscle and your smooth muscle. That's, part of the systems that it works in. You don't have a real system of those things. But you do have a bone system, a skeletal system, that's a combination of bone and cartilage and ligaments. And a few other weird things like a vertebral disc. Your bones, in some cases, are zipped together. Is that in your skull, there's actually a bunch of bones, but only a couple of them can move. The top of your vertebrae where it intersects with your skull can move, or you can't nod your head. And your lower jaw articulates with your skull, and that moves. But other than that, the bones in your skull have what are called fixed joints. And when you're a baby, there's actually a little bit of cartilage in between. And at the intersection point of the bones, you get what's called the soft spot. You go, oh, look, you can touch their brain. No, you're touching cartilage. It's not really that vulnerable, but it allows the skull to distort coming down the birth canal. My son came out with a head shaped like a missile. The one thing they never told me, though, because I knew that was a possibility, he came out with this long pointy head. As soon as he cleared the birth canal, his skull went oing. It didn't make that sound effect, but it needed that sound effect, which is a little alarming. Sometimes it stays distorted for a while. But you've got a lot of articulation points. You've got a lot of joints that move. So we'll talk about bones. Your bones are calcium carbonate, but they tend to be coated, for people that looked at the femur in the cells and tissues lab, there's an epithelial lining around the bone. Now that one is a tough one to explain because you have to really think it through, because some people go, oh, it protects the bone. Why would a bone need to be protected? What you've got next to your bone are a bunch of muscles that are moving. And bone itself is a somewhat rough material. This epithelial sheath smooths over the surface and also produces kind of a type of fluid. There's fluids all over the place that allow things to move fairly smoothly next to one another, so that your bones are not rubbing against your muscles as your muscles move. Also, you pack some nerves and blood vessels underneath the sheath that run along the bones and through the bones as well. Bones are kind of named by shape. You got a lot of long bones. Your long bones are responsible for most of your growth. The growth hormone affects long bones more than short bones, which is why people who are growth hormone deficient, when they get to be adults, they have short arms and legs and fingers and toes, but their central skeletal system, which doesn't have a lot of long bones to it, it is more normal size. You've got some flat bones in your skull. Your pelvis is a flat bone. You've got short bones, like are in the gliding joints of your ankles and your wrist. And you have some irregular bones. Your vertebrae are pretty irregular bones. Your ribs are flat bones. Your sternum is actually, I forget how many bones it starts as. I want to say 6, but I don't think it's quite that many. That's why not everybody has the same number of bones, is that some of the bones that are supposed to be completely fused by the time you're a kid, and some people stay separate from one another. So I think the 206 to 209 is what you get as a range for the human skeleton. It turns out that a hollow cylinder is very close to as strong a support system as a solid cylinder, but it weighs less. So instead of having bone all the way through, the center of our bone is very fibrous and has marrow in it, which is more liquidy and lighter than the bone is. So it does reduce this weight of the bone. And then we use it for stuff. We have 2 types of marrow. We have the marrow everybody knows about, the red marrow, which is where your blood cells get made. But when you get to be a full adult, you're not cranking out that much blood. You're not making that many new cells. You don't need a lot of bones in the making cells business. And you don't want to solidify the bones because that would make them heavier than they need to be. So what we do in an awful lot of our adult bones, well, let me say, okay, for me, my vertebrae almost certainly has red marrow in it. My hip bones have red marrow in it. My thigh bone probably has red marrow in it, possibly in my shoulders. But the rest of my bones, if you crack them open, the marrow will be what's called yellow marrow. It has fat. We actually store fat in our marrow, which makes it, for predators, you'll see predators chew on bones and crack it open. And red marrow isn't terribly nutritious, but yellow marrow, as fat has an awful lot of calories in it, yellow marrow is more nutritious. It's a good thing to get at if you can actually crack the bones. Your bones are kind of rough, and they're made out of a material that can actually erode if you rub them with something else. It's hard, like another bone. So where your bones move on joints, you need to coat the bone on each side with something smooth, and then you put fluid in there, slippery fluid, so the bones slide past one another and don't wear away. Cartilage is, we use it for some structure like the bridge of your nose, but most places in your body, there's cartilage where these bones interact. There's cartilage where these bones interact. There's cartilage where these bones interact. It just coats the ends or the contact points of the bones so that they move past one another. In fact, people that have cartilage damage in their knees often will have to have little bits of bone cleared out, because if the cartilage is gone, the bone starts to actually chip little pieces of bone off each other where they articulate. Sometimes there's spacers between the bones, little fluid-filled spacers. You have one behind your kneecap. You have them in your finger and toe bones. That's what you pop when you pop a knuckle. Those are called bursa. Now, a bursa is a fluid-filled space. There's a bunch of bursa in your body that are not in your skeletal system, but there's a bunch of them in your skeletal system as well. And then when the bones move, you don't want them to move every which way. You need them to be held into a certain limited range of motion. And also held together would be nice. That's what ligaments do. And ligaments on a cellular level look pretty much just like tendons. They're built out of the same material. When you get near the muscle, a tendon looks different, but where you see it connect to a bone, it's almost indistinguishable from a ligament if you look at it histologically under a microscope at a section of it. Same basic material. Sometimes you can overstretch them. They don't stretch real easily, but you can overstretch them. You can make them slip from one orientation to another orientation. It happens in the ankle sometimes. And so you wind up with sprains. You can also tear them loose. You can split them. Those are pretty serious injuries. But a sprain is a ligament that's gotten basically it's gotten a little too loose, and it's damaged and it needs to repair itself. Simple hinge joint, gliding joint, ball and socket joint, pivot joint. There's a bunch of different joints that are named according to their range of motion. And there's a lot that are not simple. This is a hinge joint, but it's got some range of motion that these don't particularly have. And these have a little bit of range of motion that's not purely a hinge, but that range of motion is coming from where they articulate with your wrist. So you can limit the terminology about certain joints to range of motion, but if you actually look at how the joints move, there's a lot of variety there and a lot of overlap. Arthra, Latin for joint. Itis, inflammation. Arthritis, inflamed joints. And there's a few different types of arthritis, but the main two variations are arthritis from issues with the joints being damaged or aging, where the collagen, remember the collagen levels drop all over the place? Well, collagen is an important component in the cartilage that protects your bones from each other at joints. So as you get older, sometimes the damage there will cause inflammation. And some people's immune systems go after the collagen and cause inflammation as an immune response. That's rheumatoid arthritis. I probably will ask you a question about the various types of arthritis because your book lists them. Okay, that is the skeletal muscular system.